let us compute some more standard derivatives, which are not from first principles, but rather by applications of the properties and from the basic derivatives we have found using first principles. Okay, so combining these two, we'll get some more derivatives of elementary functions. So the ones we have not looked at so far are the other trigonometric functions. We only differentiated sine x and cos x, but there are many more, right? At least 4 more basic trigonometric functions. That is the reciprocal of sine x, cosecant x, reciprocal of cos x, that is secant x, then sine x by cos x, that is tan x, and the reciprocal of that, that is cot x. So let's find these one by one. We will start with tan x. Although that's actually a quotient, not just a reciprocal, but as a trigonometric function that is more fundamental. So derivative of, actually, so I'll leave space here to write what that is. But how do you differentiate this? How do we know, what do we know as the definition of tan x? If you're given the triangle, then you know it is the opposite side divided by adjacent side. Or in terms of sine x and cos x, you can write it as sine x divided by cos x. Yes, and then apply quotient rule, correct. So here you have u v. So you want right, what is the order? U dash v minus, yeah, uv dash, right, by v square, because v dash minus v dash by v square is a derivative. Yeah, there you get minus, so correct. So then derivative of sine x, that is cos x, and v without any differentiation, that's also cos x. Okay, minus u is sine x and v is cos x, so v dash is minus sine x, and the denominator is just v square. I'm sorry, v square meaning cos x square, so cos square x. But now this is cos square x plus sine square x divided by cos square x, which is 1 by cos square x, because cos square theta plus sine square theta is 1, basic identity. So this is 1 by cos square x, which means 1 by cos x the whole square. So that is secant square x. So this answer is secant square x. So what is derivative of secant x? Is it going to be tan square x? No, obviously not. It doesn't work like that. So to find this, secant x can be written as 1 by cos x. So either you can use quotient rule or remember that special case, which is just minus derivative of 1 by u is minus u dash by, so let me write that here to remind you. Derivative of 1 by u with respect to x is minus u dash by u square, right? Or you can use quotient rule, only that this term would be 0 because u is 1, so u dash will be 0. What is derivative of a constant? Rate of change of a constant? 0. You should know this, but also it's obvious, right? A constant is something that does not change, so its rate of change is 0. You can also get it from the derivative of x power n, for example. Constant is just x to the power of 0. Constant means if you have 1 is just x power 0. Its derivative is 0x to the power whatever, doesn't matter because 0 times anything is 0. Okay, so either from quotient rule or from this special case, this is minus u dash. U dash is derivative of cos x, which is minus sin x, divided by u square, so that's cos square x. So this is plus sin x by cos x, cos square x rather, which I will write as cos x times cos x, so that this sin x by cos x is again tan x, and then 1 by cos x remains, which is secant x. So this is secant x tan x. Okay, derivative of secant x is secant x tan x. Similarly, okay, maybe that should be homework, although I'm sure you know the answer already. So derivative of cot x, that is, you can do it in two different ways, right? Either you can write cot x as 1 by tan x and then apply this thing, or else you can basically redo what we did here, but in the other order, because cot x is cos x divided by sin x. So both of these are options. I encourage you to try both, but if you're feeling lazy, you can just do one of them and find the answer. Answer I'll write here. You already know it. It is minus cosecant square x. Okay, or another notation for cosecant square is CSC. So minus cosecant square x, more compact notation. Okay, and derivative of cosecant x, this will be what? If you look at these examples, tan x differentiation is secant square x, and secant x derivative is secant x tan x. Now, in some way, you can say that tan x is to secant x as cot x is to cosecant x. So if the derivative of cot x is minus cosecant square x, derivative of cosecant x should be, if it's like this, it should be cosecant x cot x, only that you see that there is a difference here which is minus. So you expect that there should be a minus here also, and so you should get minus cosecant x cot x. Okay, this is obviously not a valid derivation, it's just we're guessing, but if you just write cosecant x as 1 by sin x and apply the same thing here, you will get this. So verify that these two are true. Okay, so these are the remaining basic trigonometric functions derivatives. So we have sin x cos x, secant x cosecant x, tan x cot x, all the derivatives of all the basic trigonometric functions. Maybe as an additional exercise, just for practice, remember that we defined the hyperbolic sine function motivated by the formula for did I give this definition while I defined sine and cos in terms of the exponential function? E to the sine x is e to the ix plus e to the minus ix by 2i. So similarly, sin hx is defined as okay, e to the x plus e to the minus x by 2, no I anywhere. Okay, this is called hyperbolic sine function, also pronounced as sinh of x. Okay, sin h, but sinh of x is a common pronunciation. Similarly, you have cos of x, which is e to the x minus, I'm sorry, mixed up the sign here. This should be minus. Usually we write this first, cos x first. This should be minus, and this should be plus. Okay. And then remaining hyperbolic functions can be defined just in terms of these. So you have also this, which is, we are just making analogous definitions basically. And similarly, and hyperbolic cosecant, okay, which is inverse of, or not inverse, reciprocal of hyperbolic sine. So all these definitions are there, simple to understand because these are the basic things. Everything else is in terms of these two, which can finally be written in terms of these two. But try as an exercise, if you want, you can find all of their derivatives, okay. But the way you should do it is, first find the derivative of sinh of x, and you will get that in terms of cos of x. I'm not telling you what it is, but it's obvious if you look at it. You will get it in terms of cos of x. So don't leave it in the form of exponentials. So I don't want any of these answers when you do it. None of these answers should be in terms of e power x. Finally, they should be in terms of these very functions. So if you start from this or something and write it in terms of exponentials, you will get something complicated, which is, it's difficult to recognize what it's going to be, okay. So what you should do is start by differentiating only these two. Sinh of x, you will get a derivative in terms of this, and this one's derivative you'll get in terms of this. Again, remember that sin x derivative is cos x and cos x derivative is minus sin x. You can check whether the same thing happens here. You won't get exactly the same thing. You'll get something similar, but not exactly the same. And then for differentiating these, you should use these definitions, not the basic thing in terms of exponential. You should use these two and the various rules, product rule and chain rule and quotient rule and all that to get this. Only thing is that you may want the identities, that is sine square x plus cos square x is 1, but here sine actually not even that, cos square x minus sin square x is equal to 1, okay. This is the identity here, there is a minus here, so this will be equal to 1 rather than with plus. If you add them, you'll get cos 2x, just like if you do cos square theta minus sin square theta, you get cos 2 theta. So here if you add these two, you'll get cos 2x. So, and if you subtract, you'll get 1. So this will be useful in one of these. So similarly to what we did here, you will need this identity when you find these derivatives, okay. So this is just an exercise, optional. If you want practice, you can do it. You were asking for derivative of sine of x square. Do you mean sine of x square, because we already did that in chain rule, or sine square x? That's also an application of chain rule. So if you're asking sine of x square derivative, which is what that looks like, this should be 2x cos of x square, which is very basic compared to the composite of composite which we did before, right? This is just one composition. On the other hand, if you're asking for sine of x the whole square, which we usually write as sine square x, just a notation for the same thing, then derivative of sine square x is again found by chain rule. Only remember, sine square x means actually this. This is notation. Sine square x is actually sine of x the whole square. So here also we have a function of a function, but the inner function is now sine x. Here the inner function is x square. Sine is the outer function. Here sine x is the inner function and square is the outer function, right? The square is the outer function. So if you start by differentiating the innermost function, what does that give you? Sine x derivative is cos x multiplied by derivative of the outer function by considering this box as one variable. So this is just y square. What is derivative of y square? 2y with respect to y, right? So 2y. 2y means 2 into that box, that is 2 sine x. So this is cos x times 2 sine x, that is 2 sine x cos x, which is in fact sine 2x. Both of these are correct, just a different way of writing. So derivative of sine square x is sine 2x. On the other hand, derivative of sine of x square is 2x cos x square. If you have x square inside, that is never going to go away. That will remain as x square here. Here on the other hand, you have sine square x. That becomes 2 sine x cos x, which is cos 2x. Similarly, what is derivative of cos square x? Will it be cos 2x? If derivative of sine square x is sine 2x, is derivative of cos square x sine 2x? Cos 2x. Or maybe there's a minus involved, right? So maybe it is minus cos 2x. Is that correct? So surprisingly, maybe surprisingly, derivative of cos square x is also in terms of sine 2x, only with a minus sign. So it is minus sine 2x. But that shouldn't, yeah, it is minus sine 2x. That should not be surprising at all, because cos square x is just 1 minus sine square x. You can do the same type of differentiation with a chain rule, of course, but also you can just notice that cos square x is 1 minus sine square x, and 1 is a constant. So if you differentiate this, you are just differentiating this, right? And what is derivative of constant? 0. So what should the answer be? Minus derivative of sine square x, but derivative of sine square x is sine 2x. So this should be just minus sine 2x, right? You should notice those things. If you, at least after you do this procedure and get minus sine 2x as the answer, you should ask how is that related to this derivative that we found, and then at least you should realize this. So whenever you notice some pattern like this, as I've told you before, find out why the pattern is there. That is the actual interesting part of mathematics, not just memorizing these formulas. Whenever you notice a pattern, find out why that is there. Okay, sometimes there is a good reason, and if there is no good reason, recognizing that is also important. Now you can of course do it in a slightly different way. Sine of x square, we use chain rule, but you could also use product rule, because y square is y times y, right? So in general, not just for sine x square, in general, if you have derivative of let's say u square, this is actually a special case of uv rule, because it's derivative of u multiplied with u itself, right? V is equal to u. So this should give you u dash times u plus u times u dash, but both of these are same. AB is equal to BA, so u dash is equal to u dash u. So this is 2u u dash, which is what we have here, 2 sine x dx of sine x. So that way also you can get it. So in the first one, if you differentiate it, I'll just use this ad hoc notation for this indicating the derivative. Please don't write this is equal to the derivative. Okay, that's not correct. You have to write differentiation of this equal to whatever that is. Okay, so you have product rule here, and for the first two terms, so e to the minus tan x, and then for the second term, when you use product rule and you're differentiating the second term, you'll of course need chain rule. So that will be minus x square. Yeah, that's correct. What you've written is correct. minus x square secant square x, sorry, e to the power of minus tan x. That's right. And yes, second one, when you differentiate, you will get a times cos ax, and here plus a times sin ax, so a will be common. Correct. Okay. Fine. Now the third one. Okay, sorry. Parth asked whether you can multiply and divide by 1 minus e power x. You can, but that will not really simplify it. I don't think it will make it simpler to differentiate, because you still have 1 minus e power minus 1 minus e power 2x in the denominator then. Okay. Fourth one, what? Okay, fine. Yeah, it cannot be just e power minus x. You will have a denominator for sure. Okay. So here, as I said, you can do it by using quotient rule or product rule and chain rule. But then finally, okay, let's try doing that, and then let's see if we get a simpler answer in the end, so that in hindsight we should have done something else. So here, if you differentiate this without any initial rearrangement, you just apply. Okay, what I'll do is I'll apply product rule. So e to the x by 1 plus e to the x minus e to the x by 1 plus e to the x square. I'm taking this as u, this is u. So u dash v, v being 1 by 1 plus e power x, plus uv dash. So u v dash is obviously, okay, there is an additional e power x. V dash is derivative of 1 by 1 plus e power x, which by chain rule is minus e power x by 1 plus e power x the whole square. Okay. So taking LCM, which you would have got if you had done product rule also, you multiply by e power x. The first term is multiplied by e power x, and then you have here e power 2x, and then over here the LCM, which is this. And so here e power x times 1 and e power x times e power x is e power 2x, which gets cancelled with this. So you just get, okay, so it's not necessary to do this. This is also fine as an answer if I only ask you to find the derivative. But if you can, you may want to write it in the simpler form. Okay, it's just a preference. So yes, e power x by 1 plus e power x whole square is what you got. Yes, that's correct. Yes. So Atharv has asked me, you can ask that. That's correct. You can notice that if you add and subtract 1, this gets simplified. So notice that this can be written as 1 minus 1 upon 1 plus e power x. Correct? If you just do this with LCM, You just compute this, combine these two with LCM, you will get this. Or how do you notice that? Or how do you get it? You see that this is e power x, and in the denominator you have 1 plus e power x, so there is only a difference of 1. So if you add 1 here, this numerator will become denominator. But of course you cannot leave it that way. So you add 1 and then subtract 1. So then you get the same thing as a denominator in the numerator, but then minus 1. So that becomes 1 plus e power x by 1 plus e power x, which is 1, minus 1 by 1 plus e power x. Now to differentiate this, it's simpler because you don't need product rule, or you don't even need the real quotient rule, the general quotient rule. This is just reciprocal, right? So differentiating this, the first term is constant, so that becomes 0. You don't even need to write it. I'm just writing to show you. So you get 0 minus this minus derivative of 1 by 1 plus e power x, which if you remember, as I told you, an important special case of the quotient rule or chain rule is derivative of 1 by u, which is minus u dash by u square. So minus u dash by u square, in this case, this is 1 by u here, right? So derivative is u square being this, and minus u dash being minus e power x. So minus and minus cancel to give you e power x by 1 plus e power x the whole square. Okay, so no quotient rule here. And although it looks like you have almost the same number of steps here, it's actually simpler, because once you notice this, you immediately get this answer, right? Even this much elaborate writing is not necessary. You can see that this minus and the minus from differentiating the reciprocal will cancel out. So you can, as soon as you notice this, you can immediately write this. Yes, you are saying that the derivative of denominator is numerator. That's correct. But that's actually relevant when you're integrating. So if I ask you to integrate this, then you can say that integration of this is log of 1 plus e power x, because this is derivative of denominator. So it is of the form du by u, integration du by u, which is log of u. Right? But yeah, that's correct. The numerator is the derivative of the denominator, which is why you're getting this again. This e power x actually, as you can see, comes from the denominator. Okay. Now the fourth problem, has anyone done? Which is yeah, I've written it here, right? 1 by answer is e power minus x by 1 plus e power minus x whole square. Yes, basically the same thing as this, only that it's minus here. So you'll get an additional minus from there, which should go away, because yeah, you get an additional minus in this, right? You have, there's no, this minus is not there. Okay. So when you differentiate 1 by 1 plus e power minus x, you're almost doing the same thing here, from going from here to here, but you have an additional minus e power minus x and 1 minus from differentiating the reciprocal. So those will cancel out, and you'll get e power minus x by 1 plus e power minus x the whole square. You can also notice that this is exactly the same function as the third problem. If you multiply and divide by e power x, you get e power x by e power x plus 1, which is the same thing. So you already differentiated it. Okay. Even after getting the answer, you can notice it, but it's maybe more difficult to notice it then. So if you differentiate it, so not this, if you differentiate it, you will get, as you said, you get e power minus x by 1 plus e power minus x whole square. Now, if you notice a similarity here, of course, that's because this is almost the same thing except with the minus sign. But you can also see that this e power minus x being the reciprocal of e power x, you can take that common. So this is or in other words, the denominator can be multiplied by e power x the whole square, because there is a square here. So e power x the whole square. So here you get e power x plus 1 the whole square, but that has to be balanced out with its reciprocal, which is e power minus 2x. So this can be now brought to the numerator with a plus in the exponent. So that becomes e power x by e power x plus 1 the whole square, which is again the same answer because it's the same question, just written differently. So when you have e power x and this form, these kinds of things you should notice. Sometimes it simplifies the problems, especially in integration. So as later we'll do integration. So as you noticed in the previous problem, the numerator is indeed the derivative of the denominator. So you have, if you have to integrate this, it is of the form du by u integration, which is log of u. But if you are to integrate this, the derivative of denominator is not the numerator. So you cannot apply that unless you rewrite it in this form. So noticing that is important, maybe for later problems. Okay.